Okay, so let us take a look at dynamic memory allocation using new, okay, the new keyword. The new keyword is used to allocate memory dynamically, okay. So for example, let us create our integer here, and we want to allocate memory, okay. So this memory is going to be stored in this pointer, okay, called the ptr, which is our pointer, and we are going to set it equals to the new int. We are going to allocate memory for this integer, okay, for an integer, okay, enough memory for an integer, okay. So here memory is allocated on the heap, okay. It's allocated on the heap, not on the stack, okay. So this is the one that is allocated on the stack. If we say that int x equals to 10, this one is allocated on the stack, okay. This one is allocated on the stack, but this one is allocated on the heap, okay. I think you get the point, okay. So the PTR stores the address of that memory, okay. So you can assign a value like this. You can say that so for accessing a value at a pointer, we always use the reference operator, okay. And here we can also assign a value in that memory address, okay. So we can assign 10 to it like that. And let me change this one to be 20, okay, so that we don't get confused in future cases, okay. So from there, as you can see here, we can now try to access see out. Then we use the reference pointer, the reference operator pointer, okay. From there we can now go back in the terminal. We try to use to compile. After compiling, let us run our program. As you can see, we get 20, okay. So here we have dynamically created a memory address, and we have stored a value in that memory address, okay. So as you can see, so let us now take a look at deallocating memory using delete, okay. So when you are done using dynamically allocated memory, you must free it using delete, okay. You must free it, okay, to avoid memory leaks. So we use delete. We use after using our memory, okay. After using our memory, we must delete it, okay. So we must release, okay, using the delete, and we delete that memory, okay, like that, okay. And if we want to see the memory that was allocated for us, we can just use this one, ptr, like that, okay. And this one is going to give us access to that memory. We are going to see it. If we try to save, we try to go down in our terminal, we try to compile. After compiling, we try to route. As you can see, so here we get this memory address. It is the one that was allocated for us. No, it's not. So it starts from here, this 20, don't count it. So we can add this end line like that. We go in our terminal, we try to compile. After compiling, we try to run. As you can see, so this is the memory, okay, that was addressed, okay, that was created for us, okay. And we have stored 20 in it, okay, from there. And we can now release. We have released the memory, okay, at that address using the delete keyword, okay. So we have deallocated that memory, okay. So and this one releases the memory back to the system, okay. So failing to do this one causes a memory leak, as I told you, okay. So let us now take a look at dynamic memory for arrays, okay. So we can create a dynamic memory for arrays just by adding like that. Then we add the size, okay. So we want a maximum of 5 arrays like that, okay. So let's delete all these ones so that we don't. So from there we delete, okay. But do we delete like this? No, we don't delete like this, okay. So let me first explain this one. So this one allocates memory for 5 integers on the heap, okay. So to free the memory, we use the delete ptr, but we add here, we add a square brackets, pair of square brackets, okay, after the delete keyword, okay. And this one is going to deallocate memory, okay, which was allocated for this pointer to this array, okay. So I think you get it. You should notice the square brackets. They are very important, guys. They are very important, these square brackets, okay. So let us now take a look at memory leaks, okay. A memory leak happens when memory is allocated but never released, Okay, you allocate a memory but you never release it, you don't release it. Okay, that one causes a memory leak. Okay, so for example, let's take a look at this memory leak. If we try to create an integer here, we try to create a pointer ptr2 to this new, and it's going to be for an integer, and we don't use the delete to release this memory address. Okay, problems are going to come up, and we are going to cause what we call the memory leak. Okay, so the program uses more and more memory. Okay, if we don't release them, the program is going to use more and more memory. It's going to cause slower performances, and the programs may crash. Okay, so you should always delete what you allocate. Okay, so let us take a look at what is called juggling pointers. Juggling pointer is a pointer that points to memory that was already being freed. Okay, so imagine you free a memory and a pointer locates to that memory that was already freed, that does not. Okay, I think you get it. Okay, so a pointer that points to a memory that has already been freed. Okay, so for example, if we have our point at this memory, if we allocate a memory like this, and from there we use the delete, we delete ptr2, we delete that memory. Okay, and from there we can now, from there we do something like this. So from there, ptr is now doing what we call juggling. So we delete that memory, as you can see. So juggling pointer, we say that a juggling pointer is a pointer that points to a memory that has already been freed. Okay, so from there we create a memory, then we delete that memory address. Okay, so now this one ptr2 is now juggling. Okay, it's now juggling. Okay, it's now juggling. To avoid this, we should set the pointer to null ptr. Okay, so from there we can set the pointer ptr2, and we can set it now to be null ptr, like that. Okay, so we can add something here. So if we can come here. If we had something, let us try to store a variable there, ptr2. I think VS Code might not warn us. Okay, so, and we try to store 40 there. Let us wait to see. As you can see, VS Code is not warning us. It's not warning us. So let us try to compile. Let us try to wait. Okay, it has compiled successfully. Let us wait. Yeah, it has compiled very successful. Okay, but here we have freed the memory. Okay, so let us try to compile. Let us try to output cout and ptr2, but we want to access the value there. We save, we go in our terminal, we try to compile, we run, we get 40. Okay, we get 40, but as you can see, have you seen it has paused for a moment? As you can see, are you seeing it is pausing? It has paused for a moment and then it has ended. Okay, are you seeing? So this one can lead to problems. Okay, it can make our program crash. Okay, so if we come down here and we try to see out hello, like that, we save, come down here, let us see if that last code is going to be executed. As you can see, let's wait. You get it. Okay, you get it. So here it has resulted into a problem. Okay, so here we are accessing a pointer which does not exist. So let me first delete this one. Okay, this ptr, so that it doesn't confuse us. Let me comment down this line. Okay, so as you can see here, this one is not running. Okay, so we have done what we call juggling a pointer. Okay, we have created a juggling pointer right here. Okay, so we should avoid all that. Okay, so we should avoid. So to avoid this, we should set the pointer to null ptr. Okay, so at the end here, so let us set it to be equals After deleting, let us set the ptr2 to be equals to null ptr, like that. So if we save, we go in the terminal, we try to compile. After compiling, we run. Let's wait to see the output. Whoa, it doesn't run because, as you can see, this ptr no longer is set to null ptr after deleting. Okay, so this one prevents us, okay, from prevents our program from crashing. So we get a way to improvise, okay, before compiling, before executing this program in the production. Okay, so let us see how we can use and we can work with another concept, and this one that I'm going to explain is called smart pointers. Okay, so let us take a look at modern C++. Okay, so in modern C++, it provides smart pointers that automatically manage memory. Okay, so common smart pointers include the unique PTR, the shared PTR, the unique underscore PTR, and the shared PTR. For example, we can include this this one. Let us use this preprocessor hashtag include, and we want to include the memory. From there we can go down and we start using the unique. Okay, so let me delete all of these boilerplate code and we start using our modern C++. So we can say unique, as you can see, unique underscore ptr, and this case is going to be for an integer, then the name ptr. From there we say it's equals. So this one we want to use the make unique, make underscore unique, no underscore unique, like that. As you can see, we get access to that. Make underscore unique, we want for the integer, and we want it to be 10. Okay, underscore unique 10. So this one, what does it do? So smart pointers automatically free memory when they go out of scope. Okay, and this one reduces errors. Okay, so this one we shall go into, and I will go deep and explain this part in future videos. Okay, but make sure you watch that video. I will update you when I release that part, okay, of the advanced C++. Okay, but right now if you are writing programs that are memory should I call it that are memory that are need in memory, that they need access to memory. Okay, most especially those who are doing embedded systems. Okay, you need to learn this advanced C++. But right now this part is I want to cater for beginners. That's why I'm not going to go into this advanced part of C++ memory allocation. Okay, so we shall see that in advanced concepts. Okay, so let us see what the reasons, okay, why memory management is important. Okay, so the first reason is that this prevents crashes. Okay, so memory management prevents crashes, and it also improves performance. Okay, it improves performance 100%. Okay, so and it also avoids memory leaks. Okay, I've been talking about memory leaks. Okay, but you should know that. Okay, so and memory management also makes your program reliable, guys. Okay, so if you know memory management, your program becomes reliable and efficient. Okay, so poor memory management can cause serious bugs that are hard to fix. Okay, so thank you.